So, a little bit about me. I work with Elizabeth on the Applied Physics program as well. I'm a theoretical physicist by background. I work on ideas like the beginnings of the universe, gravity, fundamental physics, that kind of thing. More from a kind of big picture point of view than a quantum picture point of view. But actually, as I'll hopefully explain to you, there are a lot of connections between that. I'm also somebody who, since my upbringing, has always been in contact with faith. I'm quite a strong believer that faith, and particularly the religion of Islam, is one of the perspectives in which I kind of view everything in. What I would like to do, let's see how far I get. I might pose more questions than I will answer, but that's, as any good scientist should do, is kind of guide you through how science views some of these very big questions, such as what, you know, the moment of creation and the beginnings of the universe, but also the kind of questions that science appears unable to answer, and maybe where other perspectives are helpful. So, cosmology as a science is concerned with the beginnings and the evolution of the universe from, if you like, the t=0 point of view, the Big Bang. For a long time, people actually considered that human beings and the Earth was the centre of the universe. Then we abandoned that notion, but we believed that time was everlasting. And then as even in the middle of the 20th century, people believed that the universe was in a steady state, that everything that is and was would carry on as it is. And if we were to ever observe that galaxies were moving away from us, it might be that in the space where they had moved, new matter was created instantaneously. And this idea persisted for a long time because it was, without firm evidence to the contrary, believable. Then as we found evidence towards the leftover radiation left from the Big Bang and many other things, we were pointed towards this idea of the standard model that we have today of cosmology, involving a Big Bang and a matter content of the universe. It's actually very unlike what we see. The matter that we see around us makes up a very small constituent, we believe, of the universe. The problem is we don't know what the rest of it's made of, actually, but that's another story entirely. But we've also got to kind of place this in context. Where are the limits of our knowledge and where's the limits of our reasoning? Do we know what we don't know? And are we sure that we know what we know? And actually, those kind of questions are very unanswered, I think, in science, particularly in an area like this one. So I quite like this picture by an unknown artist. It was a wood engraving that appeared in a book by Camille Florian called L'Atmosphère, in the end of the 19th century. And this is a kind of colour version of that that's been created. And basically it points to a believer poking their head through the firmament, the boundary between this world and perhaps, you know, the unseen heavens, etc. And any good cosmologist is essentially trying to do this. They're trying to move out of the realm of everything that we see here, and even everything that we see in our solar system, in our galaxy, and not just everything that we can see, but to go back in time to try and reconstruct where we are and how we got here. But in a sense, it's even more than that. We're trying to understand things that we could never directly observe, but by assuming some of those things, get to a point where we can not just see everything that we see, but try and predict where we're going. Sounds a bit kind of, you know, new earthy in some sense, but there was a long period in the standard theory of cosmology where we believed that we were perhaps heading for a big crunch as well as a big bang. So if we can speak about the end of the universe in that sense, we must be concerned with these questions. The origins and the finale are all, you know, very, very important things for all of us. So I'm always intrigued by this picture because where is the boundary? It's probably not a physical boundary. Perhaps it is, but probably not. So in some sense, it's a boundary of reality, a boundary of consciousness, a boundary of where. And do we even know, if we like, do we even know where the boundary is? So kind of a brief picture of the universe. and cosmology. So we believe now, backed up by evidence that I'll go into, that there were big bangs. I say big bangs because the standard picture that a lot of people have about the universe is that there was some massive explosion and all the universe expanded from that point in space and time. Sadly, that's not quite true, as I've discovered every time I speak to the public about science. At every point in space and time, there were big bangs, and the universe expanded on from every point in space and time. So we shouldn't really speak of a big bang, we should speak of an infinite series of big bangs. But the idea is roughly speaking the same, that every point in space and time was constantly expanding outwards. What caused that expansion is a good question. From that, we can then speak about, as a cosmologist, everything very, very early, so basically the first 3 minutes of the universe. Then from 3 minutes, the next thing that, the kind of things that start to happen are all of the fundamental forces that we see nowadays are all very separate. Gravity, electromagnetism, as Elizabeth was talking about, the things that hold atoms together, the things that cause radioactivity, they're all very separate things. And case in point, when we teach it to students, we can teach one bit at one point because it's actually relatively easier to understand, and we have to leave some things to a bit later when they develop more mathematical tools and more physical understanding, because it's harder to understand. But once upon a time, all these forces were together. And then as the universe expanded and cooled down, they separated. We also believe there's a period in the beginning of the universe called cosmic expansion. In the space of 10 to the minus 34 seconds, so that's decimal point and 33 zeros, the universe expanded tremendously quickly. And again, this was one of these ideas that people came to slowly, based on evidence. If we look in the sky at the leftover heat from the Big Bang, we find that too much of that heat appears to have been too closely correlated, in the sense that it appears that one bit of the sky was talking to another bit of the sky. The problem is if you take the age of the universe from evidence and you extract back, those two bits of the sky shouldn't have been in contact with one another. So there must have been a region where everything was in contact and then it massively expanded. But for a long time, this was an idea that had no kind of sound basis in fact, until more and more evidence turned up that suggested that it was true. But again, nobody really knows why. And it's these kind of assumptions that a lot of people feel very unhappy about cosmology. Science that you can do in the lab, people feel very happy about. You can do something concrete, you can have an idea, you can test it, you can change your experiment and see if you get a different result. When we're speaking about cosmology, we can't do the experiment again. So we have to ground our ideas in things that we can measure and things that are completely forbidden by experiment. The other things that obviously can happen is that we believe that matter and antimatter all existed at the beginning of the universe, and eventually matter won. That's why we're all here. These ideas that the first atoms formed, the things that glue together the atoms, kind of hung around. Neutrons formed, atoms formed, and then the late time stuff, if you like. So that's the first 3 minutes. Then from 3 minutes to 20 minutes, the first atoms formed. From 20 minutes to 330,000 years, the universe did very little except expand. Still quite hot. At 330,000 years, light and matter separated from one another, if you like. And that's the key, one of the key observations from cosmology. We call it the cosmic microwave background. It tells us what the matter distribution is at that time. We can measure that cosmic microwave background today at 3 degrees of heat, of leftover heat, and I'll show you a picture of it. The problem is that we can't ever see further back than that point. Everything beyond that point is lost to us, just from the fluctuations of that temperature. Whether we can speak about what was going on there, we have to be a little bit careful about. But directly speaking, we want to go and look at the picture in the sky at that point. We can't see further back than that. Then we look at this idea of structure formation. So the universe was very, still in terms of cosmic scales, still quite small and expanding. But we had to get from a relatively smooth, hot universe to something that's very lumpy today and cold. And so that's this idea of structure formation. And then the bit that most cosmologists leave is, the rest of everything else. Life forming, planets forming, solar systems forming. We call it the cosmic dark ages. Cosmology tells us that these processes take 13.8 billion years, nearly 14 billion years. A lot of people say to me, well, how do you know that? And the answer to that question is, well, you put it into your model, you see what the model predicts, and the prediction from the model that closely matches what we see matches that number. So we can feel confident that number is at least a close approximation to reality. In fact, that number was 13.7 billion years until a recent satellite took new observations, much more precise observations, and gave us a figure like that. But for a lot of people, this is a number that's so crazily big, they don't really have an appreciation of it. So it's a pictorial sketch if we like. So we can see everything that we like as we look further and further back, and we're waiting for this light from further and further back in the universe to reach us. But the furthest back that we can see, this afterglow light pattern, 400,000 years, that's as far back as we can see. We would love to see what was going on right at the beginning, but in fact we can't. Yet, by assuming that various processes did happen, those appear to be the only ways in which we can proceed. The set of conditions to actually make a universe that created the matter that we see today is actually very narrow. It's where these idea of anthropological principles often arise from. The physicist and part philosopher John Barrow at Cambridge speaks a lot about the anthropological principle, because from just a pure probabilistic point of view, if you take the space of all of the numbers speaking about the beginning of the universe, the chance, if you like, if you were rolling a dice and waiting for those numbers to appear, is tiny. Is absolutely tiny. Now, whether that appeals to a picture involving God and faith is another story, but just purely on the numbers, to actually make the universe we see today is quite unlikely. And of course, this then makes lots of scientists appeal to mechanisms or ideas that basically want to guide you towards these conditions that we have. But then there must be a reason why there's a mechanism to guide you towards. So there's something deeper than just saying the universe was formed and we are here. Okay? There is something more to it than that. And of course, all good scientists need to mix theory with experiment. I don't go and do experiments myself, but I speak to experimentalists all the time, and I'm usually telling them where to look and what to look for, and then they go away and measure it, and they say, oh, you're crazy, we didn't see anything, oh wow, we saw something new. And what we can carefully do is take measurements of temperature. We can take measurements of polarization. So polarization basically is telling you in what direction is your light wave pointing. We can look at the redshifting of light. So redshifting is a very everyday process. You hear an ambulance drive past you, you'll hear that the pitch of the ambulance siren, when the siren is on, off to save someone or go to hospital, the pitch changes. The same thing is true with light. And if objects move away from us, they get redshifted, and if they move towards us, they get blue shifted. So we can observe the redshifting of the light. So even though we can observe the light, we can also infer from that the movement of the body that's giving the light. So that's more of an indirect measurement, but we can observe it. And we're looking for gravitational radiation. We're looking for ripples in space-time, if you like. You can imagine a pond, and the ducks on the pond make ripples. We can imagine that there are these ripples in space-time. So we're still looking for these, because they're actually very, very weak, but we expect in the next 5 to 10 years to see them. So the more evidence that we accrue that these things happen, the more confident we feel about our theories. But still, there's a series of assumptions. As Elizabeth mentioned, every physical theory has this series of assumptions underlying them. And often, the simplest set of assumptions is the one that wins, but that doesn't give you an impression of where did the assumptions come from. And as I say, cosmology is now very much a precision, data-intensive area of physics. So this is the latest picture of the temperature fluctuations in the Big Bang. So basically, you have to picture that anywhere you look in the sky, you see 3 degrees of radiation. And some bits of the sky are a little bit hotter or a little bit colder than those 3 degrees. The amount they're a little bit hotter or colder is 10,000ths of a degree or less. So you need a very, very sensitive instrument to do it. And that's why this wasn't observed in this detail until about a year ago. The first satellite that went up and observed this was in the 90s. The next one that made a better observation was in the 2000s, and we've just managed to get this picture now. So we can infer a lot from this. We can infer a tremendous amount from this, and every time that we develop a physical theory and then ask if this picture, amongst others, matches everything that we see that it does. Any good scientists know that if you make a graph of something, you should put error bars on it. You should say how much do you trust the data that you took at that point. You take 10 measurements, and probably the 10 measurements are not all going to be the same. There's going to be some range of those measurements. Well, for most of the points on this graph, the error bars are smaller than the width of the point that you make them. So we can feel very confident that the theoretical prediction and the experimental observation match one another. This picture, though, is still incomplete. There are a couple of points on this that are completely far away from theory, and still nobody knows why. So we develop theory and refine theory and refine theory and refine theory. And still, there are points that don't match. So there's still work to be done in cosmology. So there's work on the theory, there's also work on the assumptions. And the assumptions kind of, if you go back to the very first question, well, there was a big bang, but what banged, if you like? Where did this moment of creation come from? Moment of creation is not a typical way that people frame the Big Bang problem in theoretical physics, but it's a perfectly valid one. And what does physics say about it? What does faith say about it? And how much is it possible to mix the two? Do they naturally keep themselves in each corner, or do they naturally want to come together? And is there a conflict? And I would say that probably there's a mixture of all of that, actually. I would say for sure that they don't stay in their corners. This is very much an area of physics where you see a big intersection between theology, faith, reason, science, and all of these ideas. So for instance, we had a Big Bang and then reality as we know it came into being. Or is it just space as we know it came into being? What about time? What about, what is our notion of reality? Is it purely geometric? Is it, as Einstein said, an illusion? Are we some interacting quantum system where everything is not as solid and as real as we would like it to be, and it's just a series of assumptions? What is space and time, and are they fundamental? The simple answer is in mathematics, space and time is fundamental. In physics, no one's really sure. There are many, many models currently for how to mix together quantum theory and gravity, because this remains one of the big unanswered questions. We can draw together the fundamental forces involving atoms, the nuclear strong force and the nuclear weak force. They mix quite nicely. We can even bring in electromagnetism. And it's those kinds of joining togethers that we can easily detect in a particle accelerator like the Large Hadron Collider at CERN. And a couple of years ago they managed to find this long-awaited Higgs boson, and that was a real triumph for science because this particle had been predicted for almost 50 years. And they just needed a big enough accelerator to find it. And when they did, they felt very comfortable that every prediction that they made about their theory, by joining these three forces together and writing them in the same quantum language, worked. The problem is we have no idea how to do it for gravity. Never mind testing it, we have no idea how to join it together. And attempts to do so result in mathematical garbage. So the question that a lot of people start to wonder is, okay, how do I treat my continuous things? As Elizabeth mentioned, for instance, time appears to be continuous. But what if time wasn't continuous? What if time was, in some sense, like the sands of time? It was granular. And what we observe is, because our reaction times are fixed at some certain level, that maybe time is an illusion. These are questions that people have been wondering for a long time. So from a strictly mathematical geometric point of view, yes, space and time are the fundamentals that we need. But that's because Euclid and others decided that that was the way it was, and we stuck rigidly for many, many centuries to this idea of flat geometry. But does that mean it's fundamental? Probably not. Probably there is some underlying structure, physically at least. Are there different planes of existence, or are there different dimensions? Could there be worlds amongst us? Well, there could very well easily be hidden worlds amongst us, hidden away in the extra dimensions. There could even be beings living in those worlds. Those are not far-out thoughts. They're very realistic thoughts. Whether it's actually the case, who knows? But again, from a probability point of view, it's not even unlikely. It's just a question that perhaps we can't answer. But it's perfectly believable to have dimensions here, and them being nowhere near each other. A good one from a kind of everyday perspective is there an arrow of time? We appear to see that if I take a teapot and I drop it, it smashes into 1,000 pieces. The entropy of the system goes up. I can't reconstruct it. So there appears to be that arrow, but at the same time, the laws of physics are pretty much time symmetric. They appear to run the same way forwards and backwards. So where does that arrow come in? is that part of this idea of existence. Space appears to be, in some sense, traversable, going forwards and going backwards, in a way that time doesn't appear to be. But is that our notion an illusion? And is it just us that appears to be stuck with this idea of one way of time? It's a question. And then we can even speak about exactly that moment of creation. We believe that at the beginning of the universe there was a singularity, like the singularity in a black hole. A point of infinite energy density, matter density. But by definition, they're beyond the laws of physics. They are. People can't speak about the singularity. In fact, the only problem, other than the not quite matching observations bit that we're still trying to work out, the only problem with the Big Bang theory is the Big Bang itself. Because scientists don't like a point they can't understand. They're trying to, in some sense, get a reasoning for how to understand everything. So is the singularity the ultimate cop-out? Yes, okay, we can explain everything, just not the thing we need to explain. We can explain everything afterwards. And in fact, there are models of the universe which satisfy a so-called no-boundary proposal, which make the singularity problem redundant, which I'll come to in a second. And I think the idea of the Big Bang and of this moment of creation is a very popular one because it naturally brings us back to this idea of a first mover. That in order for the universe to have started with this Big Bang, even if there are cycles of time and Big Bangs and Big Crunches, in order for that to have happened, there must have been a first mover in some people's minds. Now, I'll take you to a quote that Hawking said in his book, A Brief History of Time. So Hawking was working for a long time, so his PhD thesis was on the singularities at the beginning of space-time, and then he was naturally interested in investigating the properties of black holes using these mathematical ideas of singularities. And he developed these ideas of Hawking radiation and all of the things that became very well known for in the scientific community. A lot of what is known, I think, in the popular science community is the universe stuff, and his book, The Brief History of Time, spent a long time in the Times bestseller list for that reason. So in 1981, my interest in questions about the origin and the fate of the universe was reawakened when I attended a conference on cosmology organised by Jesuits in the Vatican. At the end of the conference, the participants were granted an audience with the Pope, and he told us it was all right to study the evolution of the universe after the Big Bang, but we should not inquire into the Big Bang itself, because that was the moment of creation and therefore the work of God. I was glad that he didn't know the subject of the talk that I had just given at the conference, the possibility that space-time was finite but had no boundary. This means it had no beginning, no moment of creation. So there are certainly people, I have to say, these days Hawking still believes in a no-boundary principle, but not exactly in the same way that he suggests there. So there is actually still a moment of creation in his current theory. But this is certainly a very interesting way in which religious figures at the time and scientists, one, were speaking to one another in the 80s, more than 30 years ago, but also how they pictured things. Don't talk about the moment of creation itself. That's the work of God. Well, it's not that Hawking was saying, no, it's not the moment of creation. He's saying, well, I'm not entirely sure I'm so attached to the Big Bang itself. I'm just attached to explaining everything I see in a way that perhaps, I mean, I wouldn't want to, speak for the Jesuits in the Vatican and the Pope, but perhaps they're a bit more attached to this moment of creation as a scientific idea because it's attached to the work of God. So, and Hawking has obviously later written a book in the last, I can't remember what it was, 4 or 5 years ago now, speaking about why we don't need a God at all, and actually the universe can be self-existing on its own just with the laws of physics. Now, a kind of similar take on things from my point of view is that Einstein postulated his special theory of relativity, and he did it not by saying we get these weird effects that we do see, but by arguing that there are just some basic principles, and from that everything that we see follows on. And the basic principles of relativity are the invariance of c, the speed of light. So the speed of light has the same value in every frame of reference that we look at. So inertial reference frames are just basically imagining that you're moving at rest or at a constant speed. Okay, there are no forces acting on you. And that the laws of physics are always the same in each one of those reference frames. So we're all sat here and we're observing physics in our lab here. You're on a moving train, but the train is moving at a constant speed. We would see exactly the same laws of physics and we would see exactly the same speed of light. Now, by taking that on board, what we actually find is that moving clocks run slow. We actually find that moving rulers shrink. And we find that actually something that appears to be simultaneous in one frame doesn't have to be simultaneous in another. And this confuses year upon year upon year of physics students when they first learn special relativity. I'm sure it confused me and Elizabeth when we first learned it. And even now, when I think about it, sometimes I get, in my mind contradictions. Yeah, but hang on, what does that mean? And how does, why should that be? But we feel happy with these ideas because we can test them. We can test that moving clocks run slow, we can test that moving rulers shrink, and we can even test the lack of simultaneity in different reference frames. And they appear to be true. And therefore we feel very happy that Einstein, sat there working his patent office in Switzerland, was a genius. And then 10 years, so that was in 1905 that he published this idea. 10 years later, which is 100 years now, 1915, he published his general theory of relativity and argued that nature is even weirder than this. This is just without forces involved. You put forces in gravity, nature becomes even weirder. But we use those ideas every day. Those of you who have smartphones and need to get somewhere often use the maps function, and that uses a GPS. Without Einstein's laws, your GPS wouldn't work. It would be picking the wrong location every day. It would be about 800 meters out of sync every day since the satellites were launched. So we feel very happy that these are the right ideas, that we're describing reality very well, but why? Where did they come from? This idea that, we set our clocks together and then I sit here and you run away and go off to a distant planet and come back, they should be the same. It's a very intuitive, everyday idea. Now, physicists long abandoned this idea of intuition, similarly with quantum physics. They similarly abandon this because, again, it appears to match reality. Entanglement really does work, and it underpins a lot of communication systems nowadays. But it's totally weird. So how far away can we be as observers from nature to comprehend? I'm often very happy to kind of say, well, miracles, divine intervention, these are about as unlikely as other things that don't happen every day or intuitively happen every day. But actually there's a lot of things in science that shouldn't happen every day but does. So I'm not necessarily saying I want to explain them using these ideas, but from my mind as an observer of nature, there are lots of things that are not intuitive and not fitting everyday reality, but they happen. So why should they be on a different level for comprehension? And the last thing I want to kind of briefly mention is symmetry. A long-held persuasion when we develop theories of fundamental physics, which is an area that I work a lot in, is we want to make the theory elegant, mathematically elegant. We want to write down a simple equation and then a complicated equation. And we want to write down things that have a lot of symmetry. And Paul Dirac, British pioneer of quantum mechanics, who has a tombstone in Westminster Abbey, little known fact, with one of his equations on it, I think it's the only equation that sits in Westminster Abbey, spoke about God used beautiful mathematics in creating the world. Dirac was also very contradictory. He also said we don't need God, and then later on said God is obviously a mathematician, and so I don't know exactly where his beliefs lied or whether he was just trying to be provocative. I don't know. He strikes me as a provocative kind of guy. God used beautiful mathematics in creating the world, and similarly, Hawking, once upon a time, used this phrase that God created the integers. So we have this idea that numbers are very, very continuous, but some of those numbers are special to us. The primes, the integers, things like this. God created the integers. So the notion of simplicity in these theories of physics is well sought. We want to develop ideas by using the fewest number of assumptions. That's this whole idea of Occam's razor. Occam's razor has statistical probabilistic value, in fact. You can show through statistical arguments that the best theory is the one that appeals to Occam's razor. But is that in a sense just because that's a human preconception? Simplicity, symmetry, elegance. We see everything with our two eyes that can only view this much of the electromagnetic spectrum. We are biased. So are we letting our human preconceptions imprint on our perception of reality? And if we are, then we're pretty poor people to be speaking about, you know, the moment of everything. And therefore, an idea of, you know, divinity is quite a good one. Now, there is, at a basic level, an insistence that nature itself abhors a lack of elegance, but this is hand-waving. There is no scientific underpinning for that at all. There is scientific underpinning for saying, if we want to start developing theories, let's start with the elegant one and the least assumptions one, and if that doesn't work, change it. I think there's value in that, because you have to start somewhere. But people are so driven to finding symmetry, in fact. In fact, it's sometimes hard to find a job in many areas of theoretical physics unless you work on what are considered very popular or even, you know, sexy approaches to these big problems, for instance, of mixing quantum theory with gravity. Why? Because once upon a time, some people decided, in a room somewhere, I'm sure, that their theory is the most elegant and symmetric one and simplistic one, so that is the path to take. So even from a selfish human point of view, that's been made, that choice has been made, but why? There's nothing in science to say that that is the approach to take. Only that there are many examples of simple, elegant, symmetric theories. There are also examples of ones that are not, a complete pain. But most of them are that way, so we feel happy that that's an approach to take. But who knows? There's no underpinning to that at all. And it's also less clear as to what are the limits of our knowledge because of that. If we take the series of assumptions, and one of them being I want an elegant symmetric theory, are we already limiting the space of theories? Probably. But again, it's not a question that's really brought up. If you go to a physics conference and you say, okay, but what if we considered this theory because it's ugly? Everyone will laugh at you. No one really questions what's the limits of our knowledge. They will question the limit of that theory to explain observation. They would even question future observations that theory predicts, and maybe take a bet on whether it would be right or wrong. But to question the limit of the knowledge in the theory, people feel much less comfortable to do that. And I was going to list a few other connections that people have made. My favourite one is weighing the soul. Take a live person on the deathbed, find the mass, talk to them 3 days later, and see, you know, how much the soul weighed. Is that the right approach to take, to mix theology, religion, and science? I don't think so. I mean, but that's my personal view. And there are these, you know, quantum meaning of consciousness, searching for heaven and hell in a parallel universe, attempts at divinity within a physical framework. I have seen papers with those titles. And I'm not saying they're bad reads necessarily. Some of them were very interesting. Whether they were actually getting to the thing that they were looking for, I'm not really sure I could say they were. But the idea that they presented was novel in many cases. I mean, one of them was complete crackpot, but certainly divinity within a physical framework, there were some interesting ideas in that. So there is a move towards this, but it's still a very underdeveloped area, I would say. And so I would say, you know, in conclusion, science and faith can provide us with very different pictures. For instance, to see this issue of the moment of creation, the moments. And I think the virtue of abstract thought is really good. We need abstract thought when we think about faith and theology, and we need abstract thought when we think about science. And as an abstract thinker, it's not hard for me to imagine these very crazy ideas that a lot of people have a problem with. But only because I had a training in thinking, well, there are lots of things I can't touch and see physically. I don't have a problem with that. So, but that's kind of my thoughts on things, so thank you very much.